So, good morning everybody again, and now we are going to start our lecture. Today we are going to discuss some channel models that will be useful for us in discussion of the future topics such as channel filters, channel equalizers, yes, and etc. So basically, before that, we need to actually understand what happens with our signal in the channel. So, um, if you had previously this material in bachelor level course, that is good. If not, because I'm not really sure it was given this way, I have started like just for 2 years reading this course for bachelor level students and started giving them this material, but I don't know if it was given before. So at any rate, I think it's useful to remember the presentation is, how to say, made from pieces of the bachelor level course, but I will excuse me if you hear some noise. This is my dog, and yes, as I said, I will make this presentation in a single PDF file that will be uploaded in the course description. Yes. So, what about the models that we are going to discuss? First of all, in short, let me remind you that we are performing a lot of signal processing and transformations in our transmitter. And then we have signal being transmitted. Usually we are talking about some kind of modulation, yes, which is part of this transmitter. And then we have this channel, yes. There are multiple things happening to this signal we are going to transmit to the receiver in this channel. And today our focus is this channel. Yes, what happens in this channel. So you already know that we have noise and other types of interference, but also channel is limiting the bandwidth of our signal. Also, it may have some reflections and diffraction, yes, to cripple our signal, to make it detected incorrectly, yes. This is related to multipath, some intersymbol interference, and so forth. So what we now today discussing is different kinds of models for channels, because all these, how to say, effects I have mentioned right now can be more or less expressed in different locations, in different systems, depending on whether we are moving or we are not moving. Yes, all that, of course, depends on the system. If we are using wireless transmission, if we are using cable, optical fiber, and stuff like that. Yes, so these models can be very different, and they will represent the channel we are using. So the channel can also be very different, yes, in real telecommunication systems. So we are going to discuss continuous channel models and discrete time channel models, yes. Well, for discrete channel models, we are going to give some very short and brief introduction, because we'll be not really using much of them. Well, maybe for now at least, but once we get to these discrete signals and discrete channels, we'll have more details about channel with memory, yes, because otherwise channel without memory is quite simple and pretty straightforward. So for continuous channel models, we are having ideal channel. So this channel has no noise, Gaussian channel. So the same thing as ideal channel plus noise, Gaussian channel with unknown phase, and fading channel. So basically we are going to start with ideal channels and gradually move through from the simplest model to the most complex and more advanced model, and which we will accordingly also, how to say, try and model next week in Octave. Yes. So let us start with the ideal channel. So for ideal channel, we still have some, how to say it, factors, some effects that change our signal. We are in no way speaking of ideal channel as the channel that doesn't do anything to our signal. However, yes, the effects of the ideal channel are such that our signal is not really disrupted much. Yes, so what we have here is this attenuation, yes, this loss of energy for signal, which is constant. Yes, so basically gamma is constant, and usually it is also smaller than 1, meaning that our signal loses some energy when it is traveling. So this depends greatly on communication system, on antenna and stuff like that. However, in general case, we can describe this as the roughly as the function of the type 1 divided by r squared, where r is distance. Yes, so here we have distance in meters, for example, and accordingly it will look something like this. Yes, it will gradually decrease and will really never reach 0. Yes, but will asymptotically approach 0. Yes, so the higher is the distance, the lower our signal amplitude will be. Now you know from communications theory probably that there is somewhere here also some threshold, which is called sensitivity. Yes, so beyond this sensitivity, our signals cannot be really received. It is important that this signal value doesn't decrease below this sensitivity level. Otherwise, it will be undistinguishable from noise, which we don't currently have here. Yes, so without noise, but our, how to say, detector in the receiver will still make mistakes if the signal is too weak. Yes, so that's basically still the issue, that signal becomes weak. Also, once we add noise, you will see that actually the problem is not in the noise itself, but in this attenuation and this loss, path loss, which is called. Yes, so basically we can describe it as path loss of the signal. And accordingly, because of this path loss, noise is something that we should worry about. So the main problem is with this path loss. So currently we assume that it is constant value, but in future models we'll discuss today, it will be a variable also, yes. So in addition to losing amplitude of the signal, when signal is traveling through channel, it also has some time delay, time shift. Yes, so basically it's, for example, if we consider some amplitude phase shift keying signal when we have transmission of ones and zeros with harmonic signal or 0. Yes, so here we send, for example, 1. Here we send 0. And here we also have 0. Yes, so because of this time shift, we are going to receive signal at a little bit later time. Yes, so here we have time moment when the signal has been sent. Here we have this time moment when the signal has been received. And this difference is tau, the time shift, yes, delay of the transmitting signal. So this delay comes because of multiple factors. Well, of course, signal, even though it's being sent with the speed of light, which is very high, yes, meters per second, it still can take some time to cover a significant distance. So if the distance is great enough, then it can be significant time compared to the duration of our signals. So here we have this duration, T capital, yes, and this time shift can be important enough value compared to this duration of our signal, yes. if we are using some microseconds, nanoseconds, or maybe even picoseconds long impulses, yes, pulses. So even with the speed of light, it still can take some time on the scale of our signal length to reach the destination. But in addition to that, our channel is also band limited. Yes, so this is something also that is very important. And in this case, our band limited signal can really be considered as a filter, yes, of some kind, meaning that certain frequencies pass through our channel and certain frequencies are blocked. And each of these filters, which is a system, in fact, the linear time invariant system, which we will discuss a bit later in more details, and of which you probably already have some information known to you, yes. But, well, we'll discuss much more during our course this semester. So, and as any linear time invariant system, it has frequency response, yes, and accordingly, this frequency response is usually in a complex form. Yeah, so that's why we will need to discuss some complex signals, complex responses, complex mathematics, analytical signals, and stuff like that. So we'll talk a lot more of this later. I assume that you already have some basic understanding of this. So frequency response can be separated in two parts, which is amplitude response, that is the absolute value of this frequency response. Yes, so that is going to be modulus of the gamma from frequency, yes, and argument, which is phase frequency response, yes, so this is going to be argument of these complex, this is complex, yes, gamma response, which is described in more details here in exponential form, yes. So in this sense, our path loss is not really constant, yes, as we assumed, but well, we separate it in two parts. So basically here we have this amplitude modulus, and here we have this argument, yes, basically time delay. So for the ideal channel, we need to have strictly constant amplitude response, at least in the frequency band we are using. Yes, for example, in this particular case, from 500 Hertz to 3000 Hertz. Yes, here we have absolutely linear, absolutely constant amplitude response. And this doesn't distort signal in any way for each of the frequency. And also we need to have a linear frequency, phase frequency response, yes. So, however, you can see in black color that this is not really linear function, yes. So this will be not for ideal signal. For ideal signal, our linear phase frequency response should look like this. And the problem is that usually real channels neither have constant amplitude response, nor they have linear phase frequency response. Yes, so for that case, we already start off with something that is not really ideal. Even for cable systems, yes, we may have non-linear phase frequency response. Now, this will affect the shape of our pulse. So if, for example, we consider our channel to be some kind of filter, well, I am going to still name it as channel. Yes, and you send at the input the rectangular shape pulse, single rectangular shape pulse, you already know that it will at the output be a convolution of the input signal, so input signal multiplied with the impulse response of the input signal. Sorry, it's like vice versa. Some tau minus t integrated over time, and the result will be at s tau. Yes, s output tau, and here we have s input tau. So the impulse response affects these poles and also as well affects this limited spectrum bandwidth. Yes, so we have this delta F. In literature, it sometimes is denoted as W or B W bandwidth. Yes, as well. But in our course, we are going to refer to it specifically as delta F, like difference of the frequencies, delta, yes. And this is going to be our bandwidth denotion, yes. Also, by the way, sometimes I put additional materials in the slides, which you are welcome to study, so you can open it, yes, and study. Yes, so here we can see more details, yes. Again, you are not really required to study them, but you are welcome to. And by the way, I'm going to use this material now to explain this delay. Yes, so how does it affect the shape and why? And why, even though the amplitude of our signal is not really changed, then the output of the signal will look something like in this particular case, something like, I don't know, something like this, yes? Why our rectangular pulse loses its shape? Well, it's really related to the spectrum of the signal. And because basically, as you know, for rectangular pulses, if, for example, they have zero average, so here we have like minus 1, here we have plus 1, and the average is 0, and we have them repeating all over up to infinity. 1 minus 1, 1 minus 1. Yes, so the mean value, or how to say it, yes, its mean average value, yes, is 0. Yes, if we have them repeating up to infinity. And the spectrum of such signal is usually something like sinc function. Yes, so here we have first harmonic. For example, somewhere here we are going to have third harmonic. Here we have second harmonic. Then we have fifth harmonic and stuff like that. And our filter keeps only the first harmonic. Yes, which basically almost relates to harmonic oscillations of the same frequency as for this Mander signal, yes, as for these rectangular pulse shape signals. So that is happening because we are limiting the spectrum, which in theory is infinitely wide, yes. And that's one stuff. Now, however, if we will have longer pulses, yes, so for example, now this is still our channel, but now we send these pulses as longer rectangular pulses. Then the spectrum will be more condensed, more narrow, yes, like this, for example. And we will accordingly have almost two components passing through the filter. And therefore, our rectangular shape will have some smaller oscillations like this. Yes, it still will not be completely rectangular signal, but now also we will have this phase response joining the problem. So if we have multiple components, as you know already from the course, yes, Fourier transform, that we can, how to say, uh, well, write down Fourier series or Fourier transform of some arbitrary form signal as a superposition of multiple harmonic signals. Yes, so here you need to repeat a little bit maybe on Fourier basic idea, But the idea is that any kind of the signal can be written as infinite sum of harmonic signals with different frequencies and different amplitudes and different initial phases. Yes, so that basically makes up that spectrum or spectral density, whichever signals we are using. And this is something we need to consider when we choose the signals or signal channel. Yes, so in the ideal case, our channel should have enough of the bandwidth to actually pass the most important part of our spectrum. Yes, if that happens, then we are fine, and our signal's shape will not be distorted too much, and we'll still be able to see which one is 1 and which one is 0. Now, it will come a lot more to that, and we'll start discussing that very soon in a few lectures, yes, that actually not any filter will be fine, yes, and we'll actually have to make some corrections to the signal after channel just to make sure we have this ideal channel frequency response. So this is not provided to us automatically. What we do in practice usually is that we have channel with something that is not as good as this, and then we have to make some corrector or equalizer, yes, for example. Then using them both, this equalizer will improve the channel, and together they will provide us with this ideal channel response. Yes. However, as you still know, there will be also noise and stuff like that, but I'm a little bit running ahead of time. So for amplitude, I think it's very clear, yes, that this actually multiplies with each spectral component. So if our signal S of t is something like, I don't know, U1 multiplied with sin omega 1 t plus U2 multiplied by sin of omega 2 and so forth. And accordingly, for example, omega 1 is somewhere here, then this component passes through signal through channel with this attenuation, which is 1, yes, and omega 2, for example, is here. Then only half of the amplitude for omega 2 will pass through such a channel, yes. And accordingly, if we have omega 3 somewhere here, it will have 0 amplification, yes. So basically, it will not pass at all. It will be blocked. So that's how filters work, yes. And considering the signal consists of multiple harmonics, that's how amplitude response is affecting it. But it's just amplitude response. Now, we also have this time delay. This time delay actually, so if we have at the input of the channel, let us write it here, input of the channel, we have some U1 of sin omega 1 t. Then at the output, we are going to have also this gamma of frequency, yes, parameter value multiplied to our amplitude. And also in brackets, we are going to have this time shift caused by this phase, yes, difference. So this is going to be this VF. Well, actually, in this case, I'm going to write this in more details, like it is 2PF1, because here we have frequency linear, and well, it's better than to use linear frequency everywhere. 2PF1, yes. And accordingly, what does happen with this? This phase, as you can see, is different for each frequency. But what does it really lead to? And here we can see this material I have shared with you, and which I used to make some pictures also. Yes. Okay, I'm sorry. So I am back. Once again, apologize, but will be no more further distractions today. So for the phase, and as you can see here, we have different frequencies. Yes, so basically we have frequency of 1 Hz for this first signal and frequency of 2 Hz for this signal. Now, even though phase shift is equal, yes, so for example, if we consider our picture here, then we have this phase shift equal for different frequencies. So here we have 1 Hz, for example, yes, of course, here you can see that 1 Hz is somewhere here and 2 Hz is somewhere here. But anyway, yes, and 2 Hz is also here. And for example, yes, it is minus P divided by 2. Then both of these frequencies will have this argument, this angle, increased by the same amount. However, yes, this phase shift will be different time. Yes, it will take different time for this phase shift to happen. So in red color, you can see original signal before passing through this channel with the 0 phase. Yes, so basically it is a sine wave of 2p multiplied by t. So basically frequency is 1 Hz, yes. And here we can see a harmonic signal with twice as great frequency. So it's 4p multiplied by t plus 0, yes, for red here and plus 0 here. Now for blue colored line, we have this phase shift of minus p divided by 2 happened because of the channel. And it was the same for both components. Yes, so here then we are going to have, we also assume that amplitude didn't change. Yes, so you can see amplitude was maximum +1 -1 and it's still the same. So basically the amplitude response is okay, but we have different time shifts. So basically now we are having minus p divided by 2 here and minus p divided here. Minus p divided here. But even though the phase shift is equal, so this accordingly converts our signal into minus cosine according to school trigonometrical formulas, right? And here we also get minus cosine. Yes, and as you can see, it starts from -1 and goes as a cosine. However, this originated into the time shift tau, oh, sorry, I don't know why it's so big, into this time shift tau, which is greater for the first signal than for the second signal, even though the time shift was equal. So, in order to get this second signal with the correct tau, which will be equal, yes, and the problem is that we need to shift all our components by the same amount. Yes, so ideally, each of the frequencies should have this same tau. Tau should be constant rather than depending on the frequency. Tau as a function of the frequency is really not what we want, because this will happen like this. If it is a function of frequency, then for one frequency tau is greater, for other frequency tau is smaller. That will lead accordingly to a different time it takes to travel for this signal through our channel, and accordingly it will distort our signal shape much worse and much more. So basically our rectangular pulse, instead of, for example, happening like this for linear signal, yes, it may, that would be for linear phase, yes, for this first case. And instead it might happen, I don't know, something like this Yes, if we have these cases when different components have different phase shift. In fact, we will model this situation next week in our practical exercise, and you will see for yourself that this is indeed quite important condition. So for that reason, ideal channels should have linear phase frequency response, yes, like this, so that if we return to this case, yes, then the first signal, this signal would have minus p divided by 2 phase shift, and this would have greater phase shift, for example, minus p. Yes, this way it will go even a little bit more and will start like minus sin, right, like this, yes, and will provide the same tau as here. So that's why ideal linear phase frequency response should be a linear function like this red color, yes. So I have spent so much time for this because this is really very important, yes. So this is the base of our further models, yes, and accordingly, well, I feel like we can afford to spend so much time on this, and even more so that we will return to this topic when we will talk about channel filters, about equalizers and stuff like that, which is which will be a goal for us to make this phase frequency response, a linear function. Yes. So don't worry if right now maybe you don't understand everything of that. It will come more clear during our practical exercises, during our next problems we are going to discuss. But right now it's sufficient to understand that basically this nonlinear effect of the phase response can actually cripple our shape of the output signal. So if that's clear to you, then we can proceed. Even though amplitude doesn't change, yes, it still will be distorted signal at the output of the channel, even possibly to this situation when it cannot be really read. Yes, we have some problems with detecting it. So, and this causes this time delay, yes, and we really want this time delay to be the same for each of the how to say it, frequencies, because time delay tau is actually none other than derivative of the phase frequency response, yes, derived by frequency. So if our function phase frequency response is like this, yes, then derivative, which will be tau of the frequency, should be constant. Yes, and this, for example, is a multiplied by f plus b, something like that. Then it should be equal to b, or sorry, to a. Yes, and it's actually minus. Yes. So, and this minus accordingly makes it a real delay. Yes, as you imagine, we cannot really delay signal by minus 10 milliseconds. Of course, it has to be plus 10 milliseconds. So for that reason, the phase frequency response has to have a negative slope. Yes, so it has to have negative coefficient here. That after deriving it, minus by minus gives us plus. Again, these are some mathematical details I'm now getting into, and the physical meaning is that this delay is derivative, yes, derived from the phase frequency response. And if we want to have this tau the same for each component, this phase frequency response has to be linear. Otherwise, derivative will not be a constant, and therefore our signal will be distorted. Yes, so that's in short about it. And as you can see, we spent so much time on these two slides, but don't worry, we don't have 55 slides here, and we'll go much faster from here either. Now that we have understood our main model, which will be used for all of these models. So each of these models will rely on this model, right? So basically, this was a base which we needed to understand quite well. So let us now add a little bit more to this by adding noise to this signal. As you know, to this channel. As you know, we cannot get rid of this noise in at least radio and cable communications. Well, in optics, there is somewhat better situation, but optics has also its own problems, which are probably covered in according course. For you, I'm not really strong in optics, yes, and therefore cannot really tell you what is the best, how to say, equivalent of the noise in optics, but there are different, how to say, non-homogeneous effects in the material and stuff like that, that actually also requires different models. Yes, maybe not covered by this course. But what we are talking about here is more or less related to electromagnetic waves, to current and stuff like that. Yes, so making communications with electrical signals and electromagnetic waves. So in addition to what we have discussed here, that is the constant gain, yes, or path loss, to be more precise, and the constant time shift delay. Now we also, and in addition to that, limited bandwidth, yes, now we have also random nature noise, yes, which is here, yes. Accordingly, it's getting added to our signal. As of such, we say that it is additive noise. Furthermore, we are using Gaussian distribution for this random process. So this random process has some statistical properties, and these statistical properties, such as distribution, yes, mean value, variance, yes, they all are described by Gaussian, also called normal distribution law. Hence, also, noise model is called additive Gaussian. Gaussian, and in between we also have a term called white. Yes, I'll explain right now what does it mean. But so far, additive means that we add noise to the signal. Gaussian means that the distribution of the random process is normal. Yes, and white means that no correlation is between noise values. So, for example, if we open, I don't know, Octave and generate some noise by using norm RMD function, norm RMD, yes. In fact, we are going to use it later. So it says we should load some package. If you have MATLAB, it doesn't ask you it, but well, in Octave, you have to load some packages once you launch the program. So now I'm going to make some noisy signal. I don't know, n is going to be, I wanted to first see the syntaxes of this norm RMD function. So what we need to specify is accordingly average value, yes, and sigma, which is square root of the variance. So it is standard deviation. If we do not specify it, it's automatically probably assume that mu is 1 and sigma is 1. Mu is 0 and sigma is 1. So let us check if it's working like this. No, you have to specify, yes. So basically, we need to specify 0 and 1, yes. And it generates one number in the random, how to say it, with Gaussian random distribution. So now we want to generate much more than that, yes. So we need to specify the dimensions of our of our matrix, what we want to specify, where R stands for rows, number of rows, and C stands for number of columns. So now let us specify one row with, I don't know, 10,000 values. Yes. So as you can see, it now generated these 10,000 columns, which we now can display graphically by using plot command. Yes. Also I wanted to save it as some kind of variable, so that would be n. I'm not going to display it again, so now plot n. Yes, now you can see random nature process. Yes, that is actually oscillating around 0 average value, and that has standard deviation of 1. So here we have this 1, here we have this -1, and the most of the values are within this range from -1 to +1. Yes, as you can clearly see, here we have everything like shaded in the same color. In fact, of course, there are some noisy processes which we can observe more closely if we change x limits, for example, from 0 to 100. Yes, so here you can see that it's actually noisy process. It's not like color to the same color entire area. Yes, it's just this, how to say it, scale. Yes, so you can also change the scale manually and see this random process. So what we want to see, is this really a random distribution with normal, random process with normal distribution? So for that we can use histogram function in Octave, help hist, and the hist accordingly. Yes, we can specify the signal for which to draw hist and how many bins we want to show. So basically hist n 100 bins. Yes. Now it displayed for us this distribution, which is quite close to the normal. Of course, from statistics and probability theory, you know that to get ideal distribution, you actually need infinite amount of samples. Yes, well, we don't have infinite amount of samples. We can, of course, try and increase the number of generated random values. Yes, so now we are going to have 100,000. Yes, 10 times more, and this histogram should become more smooth. And as you can see, it does become more smooth, but still is somewhat like, you know, how to say it, has some artifacts to it. Now what I want to do is actually copy it. Yes, so I'm going to cut it here. Also, I want to, okay, I want to rotate it a little bit and show you how it's related to the signal itself. Yes, so let me again generate 10,000, plot it, and now I'm having this picture. This histogram. Like this. Yes, and you can clearly see that the higher is this amplitude, well, ideally this should match, yes, but I didn't resize the picture so that it matches, but they should be in the same positions, yes. And the closer we are to 0, the more noise values are happening actually. So basically this distribution can actually be, how to say it, put horizontally to this noise signal values, random values. Yes, this distribution actually shows that the further we get from 0, for example, the here or even here, the rarer this happens. Yes, actually we never even reached 4 or -4 during entire realization. We were very close here, but it's still not -4. Yes, And there is a probability to happen for that, but this probability is decreasing as we go from 0. Yes, so this is random process. And uncorrelated means that, for example, if we consider each of the values, for example, this value, then this value in no way is depending on previous value. So this is independent value. Yes, so each time we generate this noise signal, it will be slightly different. So we can actually see if that is true by simply repeating the process. Yes, so now I'm even going to merge them into single line. Yes. And now you can see that this time we did pass -4. Yes, actually, for better visualization, we can decrease this window and run a few more times. Yes, as you can see, noise process each time changes, and in no way there is a correlation. Like, for example, here, if we mark the maximum values, yes, here we have maximums here and here, and accordingly, accordingly, minimums here, 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 here. Yes, now if we generate the same process again, there will be no pattern to these minimums or maximums. Yeah, now we can see that there are a little bit more maximums here. Yes. Well, as maximums, I mean with some specific allowance. Yes, and here much more. And they do not follow any specific pattern. So if we run again and again and again, then we will not be able to see any pattern. Yes. So that is called uncorrelated. Yes. And accordingly, that is why we call this white noise. So we can close Octave, I believe, now. And accordingly, this is quite good model to describe cable channels, direct line of sight channels for radio when we have no reflection or stuff like that. For example, you have this tower, you have this mobile device, there are no any obstacles in between you, and you receive this signal. Clearly, traveling certain distance, it attenuates, that produces this gamma. Yes, clearly it takes some time, that produces this time shift, and clearly you have this noise. Yes, now we are talking about only noise, not really other systems that can, make interference with your signal, for example, in other mobile devices, but only specifically noise. Yes, so this is quite simplified model. And as I said, noise in itself is not really that dangerous, because noise is very weak random process. Yes, if we show its, for example, no, let us maybe return our picture for here. Yes, and if we show the spectrum of the signal at this antenna transmitting side, then, for example, our spectrum will be like this. And somewhere here is the noise level. Right? So, as you can see, in no way this noise level can affect our signal strength. But because we have been traveling for a long distance, our signal at the receiving point has been attenuated. So it lost a lot of energy, and now the spectrum looks more like this. If we draw them in the same scale. Now, however, noise can impact us greatly. Yes, by the way, the odd thing is that the noise also looks like noise both in time dimension and in frequency domain, which is quite really to check if we, for example, calculate FFT of the noise, yes, and plot absolute value of it. And then it is also noise in the spectrum. However, in theory, it should be, you know, constant. Well, theory doesn't match with practice here only because we don't have infinite amount of values. That is first. Second, we are using some computer that still has some algorithm to generate random value, and it in some way still depends on previous values, so it's not really strictly white as it should be in theory. And also we have quite great variance, yes, here. Also, I think I didn't normalize, so wait a minute, we should actually normalize divided by length of n, because in Fourier transform we have this 1 divided by n sum and so forth. We'll talk about this later, yes, but there was this normalizing, and Octave, MATLAB, and so on, FFT doesn't do that by default. You have to do that manually. So if I normalize, this should get somewhat smaller numbers. Now I'm going to ylim from 0 to 100, for example. Yes, well, 100 even was too much. Yes, to 10. Even 10 is too much. Okay, 1, something like that. Now we are much closer to some constant level as it should be in theory. But still, as you can see, it still is really not constant. It has some changes. Yes, we can of course find mean value. Yes, and show it, but still not really very accurate, because not really always practice and theory match, as you know. So, and as I said, because of this situation that signal gets attenuated, noise actually can be dangerous to our signal. So here you can see that we have added to our some rectangular process some noise, yes, and detected it successfully. But if we would decrease amplitude of this signal first 10 times, yes, like gamma is 0.1, and would add the same noise, then we would have a lot of errors here. And still the noise is the same. The problem is that the signal is different, yes. So in practical work, those were practical works for bachelors, but we will have practical work number 1 for this, yes, only, which will be different than for bachelors, but we will accordingly, how to say it, assume similar things. So here I offer you to make some short break for 15 minutes because we already are discussing this material over an hour. Yes. So let us then continue at 9:45. You may leave this meeting or you can stay. It's how more convenient it is for you, whichever you decide. I'm just going to stop a record now, and then we'll resume record once we start.